Okay, hello everybody. So this is our last video for thermodynamics. I'm here at the high school recording this, so hopefully the bell, if it rings, I'll pause while the bell rings and then continue. So be ready for that. So the definition of this last part of thermodynamics is for Hess's Law, and what Hess's Law basically says is that you can take individual processes or individual reactions, and you can add up their heat of reactions, and you can get an overall sum for the heat of reaction for an overall process. And so if you have, for example, two or more processes with heats of reactions, you can add the delta H values and determine the overall delta H for an entire process. And so what this might look like in a really simple situation where we don't manipulate anything, if you were writing that down, I'll zoom out, but where we have a simple situation would be something like this, where we have, A goes to B, and it has a delta H of, 50 kilojoules. And then we have B goes to C, and it has a delta H of 100 kilojoules. Well, what if I asked you, well, what is the delta H for A goes to C? Well, if I add together the two processes, if I add together, A goes to B and B goes to C, I will get A goes to C. Now, because I added the two processes, I can also add together their delta H values. So this one was 50, this one was 100, so together it should be 150. Now that's the simplest case scenario. We add together two reactions, we get an overall delta H. Things get a little bit more complicated though, because what we're doing in a lot of cases is we're manipulating equations. We have to flip them around, we have to double them or half them, and so I walk you through some examples. Let's look at this first example here. I show you carbon monoxide, nitrogen monoxide, you form carbon dioxide and nitrogen gas, and I ask you what the delta H is. It's this highlighted equation right here. What I give you is I give you two separate processes, equations A and B down here. So I go through here in the notes and I'll walk you through this. So when I look at this, I have to change around A and B to add up to the total delta H. I look at both of these reactions. Something that I like to do that I don't write down here is I like to look for something that's unique between the A and B and my target. This I call my target up here. So when I look at A, I notice something unique to it that's not in anything else would be either the CO2 or the CO. And so here's my CO right here and my CO right here. When I look at the second equation and I look for something unique to it, I notice that there's N2 and then there's also NO. So I see there's NO and there's NO. So I inspect both of these. I'm looking for something unique. I look at equation A and I see that CO is on the left side, which is good. CO2 is on the right side, which is good. And that's good because it matches the target. So for the first equation, I don't really have to do anything to A, because A is going to stay exactly the same. So, when I look at A stays exactly the same. Now I leave A the same because one, it has the correct coefficients. There's one carbon monoxide and one carbon monoxide. There's one carbon dioxide and one carbon dioxide. For equation 2 though, for equation B, I have to do some work. First I notice is that N2 is on the wrong side. N2 is on the left here, but it should be on the right. And NO is also opposite. So the first thing I have to do is I have to flip it around. So notice, when I flip around equation B down here, I change the delta H. The delta H becomes negative instead of positive. But I'm not done yet, because in equation B, I have two NOs, and I need one. So I actually have to take equation B, and I have to cut it in half. So I have to divide equation B by 2. And when I do that, I get this for equation B. Now, when I look at this, this becomes now, instead of negative 180, it becomes negative 90.3. I'm interested in two things at the same time when I do these problems. One, I'm interested in the idea that I'm able to add up the equations to get an overall final combination equation. And I'm also interested in keeping track of the delta H values. So look at what happens. When I add this up, I get the O2's crossing out. I get CO. I get NO. I get 1/2 N2, and I get my CO2. And this matches my original. If you go back to the top here, it matches my original. Now the delta H's are easy to find. I want to find the overall total delta H for this reaction. I just have to add these two values together. I get negative 373. Now, what if I want to use heat of formation? So when I do heat of formation, I'm given an equation like this. Here's my delta H for this reaction. I don't know what it is. Delta H equals question mark. And so now I could go into table C and I can look up the heat of formations. And I will actually attach them to, did I put them in this packet? Let me just look here really quick. No, I will upload them to iTunes U for you so that you have them. So when I look at this in Appendix C, I can look up the heat of formations for each of the compounds that are in this particular equation. And I can write the correct heat of formation equations for them. So, for example, if I were to do this on the side here and manipulate it in this box, I have NH3. So I would have N2 plus H2 yields NH3. So to balance this, I need 3/2 of this, and I need 1/2 of this. Now this actually has a value. This has a value of negative 45.9. But then I look in my equation up top here. And when I look at my equation up top here, I notice that NH3, first of all, is a reactant. It's not a product. And it has a 4 in front, and this has a 1. So look at how I manipulate it in this box. I flip this equation around, and I times it by 4. Notice what happens to my delta H. I flip the delta H's sign and make it positive, and I multiply it by 4. Now, oxygen's an element by itself. By definition, the heat of formation for that is going to be 0. The next one is going to be the NO. And so when I write a heat of formation for NO, I would have N2 plus O2 yields NO. But these right here have to be halves. So I can have 1O and 1N. The delta H for this one is going to be about 90. Excuse me, let me just write that down below here. Is going to be about 90. So notice what I did with it in the box over here. If we highlight it, I times it by 4 because I have 4NO. And so that gave me around my 361. It isn't exactly 90, but it's pretty close. Then I have my last one, my water. And my water is going to be H2 plus O2 yields H2O. And again, I'm going to need to use fractions. And the delta H for this one The delta H for this one, if I work it out on my calculator, 1450.956 divided by 6 is about negative 242. So notice what I did for the water. The water's on the correct side, but it's multiplied by 6. So I multiply it by 6, and my delta H gets multiplied by 6. So now I go through and I add up all of these formulas down here. The idea trying to be that I will get an overall delta H and an overall reaction. When I add all of the reactions together, I get what I underline there. When I cross out the N2s, when I add together the O2s and cross out the H2s, I get my overall reaction from the top of the slide, and I get my negative 906. Now, imagine that I could actually do some kind of shortcut for this. Wouldn't it be nice to get some kind of shortcut? And well, we can actually do a shortcut for this, and I'm going to insert a page here and show you how to do that. So how would I do a shortcut for this? Well, it would look kind of like the following. If I have my overall reaction here that I write out, my 4NH3 plus 5O2 yields 4NO plus 6H2O. The shortcut which you learned last year, which is based on this method, says that the delta H of the reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Well, the products are NO. So remember, for NO, we had 90. So my products would be 4 times 90 plus my water was negative 242, and there's 6 of them, so times 6. Minus my reactants. My reactants were NH3. NH3 was negative 45.9 times 4. My oxygen is not included because, well, it's an element. When I do this simple math out here, I will get negative 906.2 kilojoules. Look at the difference here. When you go back and look at what I did in the long way, I wrote out the equation for each heat of formation. I then added the equations together to get the overall delta H. That is the true Hess's Law method. When I take the shortcut, I know that I was using heat of formations, and I know that I was just adding their delta H's, so I use this shortcut, which I'll highlight here, to save time. This only works for heat of formations. You can't do this if they give you reactions that are not heat of formations. You have to go the long way. But if they give you heat of formations, then you can take the shortcut. Now here's one last example. Hess's Law, example 3. Find the heat of reaction when benzene combusts. So again, I would write out a combustion reaction, and I balanced it. I balanced it using 1 mole of C6H6. You could balance it with whole numbers if you want. And then I went through and I wrote the heat of formations for each of them. And I manipulated them. So my first heat of formation is the benzene. And remember, benzene's heat of formation would be this: 6C plus 3H2 yields C6H6. And its heat of formation would be 49 kilojoules per mole. Notice what I did the liberty of. I actually took it and I reversed it, and I reversed the sign. So here's my benzene. Water, again, has its hydrogen and oxygen forming H2O. And again, the long method for this, I would start with my H2 plus my 1/2 O2 yields H2O. And this would have a negative 241.82. What I did over here, which I'm going to highlight, is I multiplied it by 3 so that it would match the equation, and I multiplied the delta H by 3. And then finally CO2, again the reaction starts as C plus O2 yields CO2, except now I multiplied it by 6. This delta H was negative 393.5. But again, just to show you here, I multiplied it by 6. I multiplied the delta H by 6. I got the total. I add up the 3 highlighted equations, and I get this. I cross out the like terms and get my balanced reaction. I add up my delta H's and get my overall. Now again, what I could do here is I could do products minus reactants. I could take the shortcut. If I take the shortcut, I'm basically just adding up the numbers without writing up the overall reactions. I like to show you the long way, and the reason why I like to do that is because sometimes you're not given heat of formations, and you're forced to actually write out the equations, and that's why I'm doing that for you. Alright, so here's a summary of Hess's Law. That's the end of this chapter. Thanks so much for watching, and tomorrow we're going to do a lab, and we'll practice some Hess's Law problems.